Welcome to the video lecture on curve sketching. We're going to start by talking about 9 different strategies for sketching graphs. Now, you don't necessarily have to do every single one of these, but most of them are probably something you're going to need to look at so that you can make a nice complete graph. So strategy number 1 is going to look at the domain and range of your function. And if you can sort of just eyeball that or have a sense of what x's and what y's your graph is going to go through, then you'll know for sure if your graph is looking correct at the end. Step 2, look for any symmetry. Sometimes this can cut down the amount of work that you have to do if you know that a graph is symmetric around the x, the y, or the origin. Step 3, find your intercepts. Find your x and your y-intercept by finding the two zeros. Usually I only do this if it's easy to solve. The y-intercept will always be easy because you can just plug in 0 for x, but sometimes finding the x-intercept is a little bit tricky. Step 4, asymptotes. Now this will only be an issue when you're dealing with a function that potentially has a fraction in it or some kind of asymptote like an e to the x kind of a function. So we will review how to do that. Step 5, find your derivatives. You need to find your first and your second derivative. Step 6, find your critical points. Find where the first derivative is 0 and d and e, and find where the second derivative is 0 and d and e. Then we're going to take those critical numbers and put them on number lines, and that's step 7. So take two number lines, one for f prime and one for f double prime, and you're going to line up all of your critical numbers on those number lines, and then you're going to test each of your intervals to see if you get plus signs or minus signs. Now remember that the first derivative, if you see a plus sign, then that indicates that your original function f is increasing. If you see any minus signs, then that's going to indicate that your original function is decreasing. On your second derivative, if you see any plus signs, then that's going to indicate where your graph is concave up, and any minus signs indicates where your graph is going to be concave down. Remember that if you have a change in signs in that first derivative, then that's going to cause you to have relative extrema. So if you have a plus on the left and a minus on the right, then you go up and then down, which means you're going to have a relative maximum at that critical number. Or if you have a minus and then a plus, then your graph goes down and then up, and that would indicate that you have a relative minimum at that critical number. If the signs don't change, then you don't have anything. For the second derivative, if your signs change and go from plus to minus or from minus to plus, then that's going to be a point of inflection. And that's only true if you have a derivative at that critical number for that second derivative. So you have to have a tangent line in the first place. But if you do, and there's a change in signs, then that's going to result in a point of inflection, where you have that change in concavity. Then once you've followed all of these steps and you've lined up your number lines, then what you're going to look for is the combination of whether or not the graph is concave up or concave down, and whether it's increasing or decreasing. And there's 4 possible shapes that you could run across. You can have your 2 concave down shapes, or your 2 concave up shapes. And the difference between these is this concave down piece on the upper left is an increasing function. This one on the right decreases. This one in the lower left decreases. And this one on the lower right increases. So based on your number lines and lining things up, you'll be able to tell which of these 4 pieces you're supposed to use, and you're going to piece them together using all of those critical numbers. And then if you need to, you can plot additional points, and usually I only do that if I'm not real confident about my graph. And you're going to also want to draw in any asymptotes that you have, and then place your graph based on your y coordinates using the correct shape. Okay, so let's try several examples. So the first one here, we have the function x squared over x squared minus 9. So we want to analyze and sketch this graph. So the first thing I'm going to do is I'm going to look for some intercepts. So let's find out some of our zeros. So to find our intercepts, I'm going to first let x be 0. And if I plug in 0 for x, then that numerator becomes 0, and the denominator becomes minus 9, which 0 divided by negative 9 is still 0. So we have a 0 at x and a 0 at y as well. So we have 0, 0 as both our x and our y-intercept. Okay, so that was easy. Now what we're going to do is notice that this fraction is a function. It's called a rational function because it's a fraction, and that is the kind of function that typically has asymptotes. So let's find our vertical asymptotes first. Now vertical asymptotes occur whenever this fraction is divisible by 0. So when is this denominator going to equal to 0? Well, that's going to happen when x is plus or minus 3. And that's because you could factor that denominator into x plus 3 and x minus 3. So those are my two vertical asymptotes. And then for my horizontal asymptote, remember the definition of a horizontal asymptote is actually the limit of this function as x goes to either positive or negative infinity. But the shortcut is to just look at the dominating terms. On top, we're dominated by an x squared. On the bottom, we're dominated by an x squared, and that's going to reduce to just 1. So that means we're going to have a horizontal asymptote at y equals to 1. Okay, so now that we have our sort of basic information, you could also look for domain and range if you like. You can also look for some symmetry. If I want to sort of jump right in with the calculus aspect of this, I'm going to use those derivatives. And for any kind of test question or homework question from this curve sketching section of your textbook, you're always going to need to show your two derivatives and show your number lines as the basis for where your graph comes from. That's going to be your proof or your justification that you know how to get that graph instead of just relying on your graphing calculator. So you must show your derivatives and show your number lines. So let's go ahead and find f prime of x. Now because we have a quotient, I'm going to use my quotient rule. So I'm going to do the bottom, low, d high, the derivative of the top is 2x, minus high times d low, the derivative of the bottom is also 2x, all over low, low. Now it's important to get this derivative as simplified as you possibly can and factored as much as you possibly can. So let's go ahead and distribute my 2x across. I'm going to get a 2x cubed minus 18x minus 2x cubed. So that means my 2x cubes are going to cancel, and I get negative 18x over x squared minus 9 quantity squared. So where are the critical points of that derivative going to be? Well, if it's a fraction, that's going to happen whenever that numerator is 0, because that's when the fraction will be 0, and this fraction will be d and e whenever that denominator is 0. So let's find out when that's going to happen. The numerator will be 0 when just x is 0. So we will have a critical point at x equals to 0. And the denominator is going to be 0 whenever that x squared minus 9 is 0, and that's going to happen at that plus and minus 3. And those are, remember, are vertical asymptotes. So they're technically not even points on my graph, but we still want to include them on our number line because that will determine the intervals where I change from increasing to decreasing and so forth. So even though they're not technically points, they still are important things we need to include on our number line analysis. So there's my first derivative and my critical points for the first derivative. Now let's go ahead and do our second derivative. So my second derivative is going to be the derivative of this fraction that I have here, and I am going to rewrite that as a product. Now you can use the quotient rule, that's perfectly fine, but what I'm going to do instead is I'm going to change this derivative, and instead of leaving it as this quotient, I'm going to move that denominator up to the top and give it a negative exponent. So now this becomes a product rule. I'm going to think of this function as my first and this as my second, and then I'm going to do first times derivative of the second plus the second times the derivative of the first. Okay? If you prefer to use a quotient rule on this, that's fine too. So first would be negative 18x times derivative of the second. I need a chain rule on that. First I'm going to take the derivative of my power. So I bring down the negative 2, and when I subtract 1 from the power, the new power will be minus 3, and what's inside stays the same, and then I multiply that by the derivative of what's inside, which will be a 2x. Now I need to add to that the second times the derivative of the first, and the derivative of negative 18x is just negative 18. So cleaning this up just a tad, we've got 18 times 2 times 2. So that's going to give me a positive 72. I've got an x times an x, which will be an x squared, and then I have that x squared minus 9 to the negative 3. And then over here I have that minus 18 x squared minus 9 to the negative 2. Now the trick to simplifying these, especially when you use a product rule like this, is usually to factor. So that's what I'm going to do. I'm going to factor out what this term here has in common with this term. Now they both were divisible by 18 because they both had that 18 involved. So I'm going to go ahead and pull out an 18. And they both have an x squared minus 9. Now this one's raised to the negative 3, this one's raised to the negative 2. You always want to factor out the smaller of the two powers, which in this case is the one that's more negative. So that's going to be this negative 3 power. So then in parentheses or brackets, we're going to write what's left over. Now all of this is gone. I pulled out an 18 from here, which leaves me with a 4, and so I'm going to have left 4x squared. Then from this second term, this 18 is gone, so I'm going to have some of these x squared minus 9's left because I didn't pull out exactly the same power. I'm also going to have that minus sign left. How many of these x squared minus 9's am I going to need? Well, I'm going to need to have exactly 1 left, because if I were to redistribute, this negative 3 plus this 1 needs to get me back to that negative 2. So this needs to be a 1 so that when I add those powers, I get back my negative 2. Okay, so I have 18, I have x squared minus 9 to the negative 3, and then in these brackets we're going to get a 4x squared minus an x squared, which is 3x squared, and when I distribute that minus across, it becomes a plus 9. Now if you want, you could factor out an additional 3 here as well. So if I did that and I pulled out a 3, that 3 times this 18 will give me a 54, and what I'd have left in these brackets would just be an x squared plus 3, and I'm going to go ahead and take this negative exponent and move it down to the bottom so it becomes a positive 3. So here is my second derivative, all nicely cleaned up and factored. So then the question is, where do I have my critical numbers of this second derivative? So that's going to be whenever this numerator is 0, to find where the fraction is 0, and where that denominator is 0, which is going to be the D&E case, when that derivative does not exist, when we're dividing by 0. So look at that numerator. When is that numerator going to become 0? Well, that's only going to happen if x squared plus 3 becomes 0, and hopefully you can see that that won't happen. If I subtract that negative 3 and try to take a square root of both sides, we're going to be taking the square root of a negative, which is not a real number. So this doesn't happen. How about where that denominator is 0? Well, that's going to happen at that plus and minus 3 again. So we do get some critical numbers at those asymptotes again. So we have critical numbers or critical points for our second derivative at just the plus and minus 3. Okay? So we've done all of our derivatives, we've found our critical points, now we're ready to make our number lines. So what we're going to do next is create a number line for f prime, and on it we're going to put -3, +3, and 0, and f prime was -18x over x squared minus 9 squared. And then for my second derivative, the only critical points I had were -3 and +3, and that second derivative was 54 times x squared plus 3 all over x squared minus 9 quantity cubed. So now we have our number lines, so what we've got to do next is test the intervals. So let's start with our first derivative. If I test -4 into this, at -4, -18 times a -4 will be positive on top. Now look at that denominator. It's a quantity squared, and whenever you square something, it becomes positive. So this denominator is always positive, so that means this quotient will be plus. Okay, so now let's go to something between 0 and -3. Let's try -1. So -18 times -1 is positive again, and that denominator is still positive. So we have a plus sign again. If I try +1, then -18 times +1 makes this numerator become negative. And that denominator is still plus, so this is now minus. And if I tried something like 4, the same exact thing would happen. -18 times 4 will be negative, and the bottom is still plus. So at 4, we also get a minus sign. Okay, so there's all of my signs. Now let's do this for our second derivative. So if I test something like -4, now 54 is obviously positive. -4, when I square that quantity, it becomes a positive 16, and 16 plus 3 is a positive 19. So everything in that numerator is actually always going to be positive no matter what I plug in, because when I square whatever my x is, it becomes positive, and then I'm just adding another positive to it and multiplying by a positive. So this time around, my numerator is always positive no matter what. However, the denominator could potentially become negative. What happens if I plug in -4? -4 quantity squared is 16, positive. 16 minus 9 is going to be 7, which is positive, and when I cube that, it stays positive. So this is plus. Now let's try something in the middle, like 0. So if I plug in 0 into the top, again, everything will be positive. On the bottom, 0 minus 9 stays negative, and when I cube a negative, it's going to stay negative. So now this inside piece is minus. And if I plug in 4, then again, that numerator will be positive. 4 squared is 16. 16 minus 9 is 7, so that's going to be positive, and it's going to stay positive when I cube. So there are all of my signs. Okay? All right, so what does this tell me? Just to kind of recap here a little bit, wherever I see plus signs on my first derivative, that's where my graph increases. So this would be the interval -infinity to -3, union -3 to 0. I like to leave out that -3 because remember, -3 is an asymptote, so it's technically not a point on my graph. So you don't want to just write it -infinity to 0, because then you're making the assumption that -3 is included on your graph, and it's not. Wherever I see minus signs on my first derivative number line, that's where I decrease. So that would be from 0 to 3, union 3 to infinity. Wherever I have changes in signs, I have relative extrema. So right here at this 0, I go plus on the left, so I rise up, and minus on the right, so I fall. So this is a max right at 0. And that's the x-coordinate. To find the y-coordinate, we would go back to our original function, and remember, when we plugged in 0, we got 0 back again. That was our intercept. So at 0, 0, we have a relative max. We don't have anything at -3 or +3 because we don't have any changes in signs there. Okay? So the only extrema that I have is that relative max. Now let's go to the second derivative. Wherever you see plus signs, that is where your original function is concave up. So that's going to be -infinity to -3, union 3 to infinity, and I'm going to be concave down in between from -3 to 3. Now normally when we see changes in sign on that second derivative number line, that means we have a point of inflection. But at these 2 points I actually don't, because -3 and 3 came about from having a derivative that did not exist. It was the DNE case. And remember, those were those vertical asymptotes again. So you can't have a point of inflection if you don't have a point. So we have no points of inflection because -3 and 3 are actually asymptotes. Okay? All right. Now that we have all of those things sort of figured out, what we're going to do next is piece together our graph. So what I'm going to do is take a look at my different regions, and I'm going to sketch in my little vertical lines. So I'll have one at -3, I'll have one here at 0, and I'll have one here at 3. Where I saw plus signs, that was where I was increasing, and where I saw minus signs, I was decreasing. On the second derivative, where I have plus signs, I'm concave up, and where I was minus, I'm concave down. So you want to have labels on each of these 4 regions. And then our choices are going to be these 4 possibilities: concave downs, concave ups, increase, decrease, decrease, increase. So concave up increasing, that would be this bottom right shape. So I want to have that shape until I hit this -3. Now keep in mind that -3 was a vertical asymptote, so we're probably going to see this rising up sharply like an asymptote. Between -3 and 0, we want to be concave down increasing. So concave down increasing is this upper left shape. So we want that until I hit 0. And then after 0, I want to be concave down decreasing, which is the other half of this hill shape. And that makes sense because remember we said we had a relative max at 0. So you should see that little hill. And then we get to 3 again, and that was another one of those vertical asymptotes. And after 3, we are concave up decreasing. So concave up decreasing is this bottom left corner, so we're going to see that shape like that. So we kind of have the pieces. All we have to do now is put it onto a graph. Okay, so the only point that we actually had was 0, 0, which was our intercept and our relative max. We did have some vertical asymptotes at -3 and +3. And if you recall from the very top, we also had a horizontal asymptote at 1. So let me sketch that in as well. It's going to be a horizontal dashed line, just like this. So now what we want to do is piece together our graph. Now on the left side of -3, we want it to be this concave up increasing shape. So think about where that arcing shape needs to be so that it fits in between our asymptotes. I couldn't do it down here because then I wouldn't be approaching that horizontal asymptote. It's going to have to start above that horizontal asymptote and arc up like this towards our vertical asymptote on the right and flattening out towards our horizontal asymptote on the left. So that's going to be this piece right here. In the middle, we want sort of that hill shape, and our maximum is right at 0. So I want to have my highest point be at that 0, and I want to come down on the left and come down on the right. So this would have to shoot down towards those vertical asymptotes just like that. And then finally we want this shape here, concave up, decreasing on the right side of 3, and again it needs to fit so that I'm not only approaching my vertical asymptote, but I'm also approaching my horizontal asymptote. So it couldn't be down here, because then I wouldn't be leveling off to 1. It needs to start up above that horizontal asymptote and then approach it as I get bigger to the right. So there is my graph. Okay? All right, that's a lot of work. These take a lot of work to do, but this is the kind of work that I would expect to see to justify where your graph is coming from. Okay, let's try another one. So here we have the function 2x squared minus 5x plus 5, all divided by x minus 2. So I always start by finding out where my intercepts are, where my vertical asymptote and my horizontal asymptotes are. If you want to explore the domain and the range and symmetry, feel free to do so. Those are sort of optional things that you can look at if you need to. So let's start with our intercepts. And I only do intercepts that are easy, and an easy one is always going to be letting x be 0. So if I let x be 0, this should tell me what my y-intercept is. So y will be, this goes to 0, this goes to 0, this goes to 0. So we're just going to have 5 over negative 2, or negative 5 halves. So we have an intercept at 0, negative 5 halves. Okay? So there's my intercept. To find the x-intercept, you would have to let this equal to 0, which is only going to happen when that numerator is 0, and that's just a quadratic equation. Sometimes if those factor nicely, then I go ahead and figure it out, but that one doesn't look like it's going to factor. You'd probably have to use your quadratic formula. So I'm not going to bother wasting time on doing that. Only find those intercepts if they're easy and quick to do. Now, because this is a fraction, that means we are going to have asymptotes probably. So you're going to have a vertical asymptote whenever that denominator is 0, and that is going to happen obviously when x is 2. So we'll have one vertical asymptote at 2. Now to find our horizontal asymptote, remember what we're technically doing is taking the limit as we go to plus or minus infinity of this fraction. But that really boils down to the dominant term on top, which would be that 2x squared, over, let me fit in my limit here, the 2x squared on top, and on the bottom, what dominates would just be that x. So if you reduce that, 2x squared over x just becomes 2x. And what's that going to do as x goes to infinity? Well, 2 times infinity is going to stay infinite. So that means we have no horizontal asymptote because this graph is not leveling out towards anything. Okay, so we're not going to have any kind of horizontal asymptote. This one actually will have what's called an oblique asymptote because the degree on top is exactly 1 more than the degree on the bottom. So just to kind of review for you how to figure that out, you would do some long division, or you could even do synthetic division to figure out what that oblique asymptote is. Again, this is sort of optional. You don't have to do this, but I just want to review with you what you could do. So if I take that denominator, x minus 2, and I divide it into my numerator, x times 2x would be 2x squared, and 2x times minus 2 would be minus 4x. When I draw my line, I have to change my signs to subtract this whole bottom row from the top row. So this becomes minus, this becomes plus, which means these guys cancel out. Negative 5x plus 4x is negative x, and I bring the 5 down. Now x times a minus 1 will be minus x, and negative 2 times negative 1 is positive 2. So when I change my signs, this becomes plus, this becomes minus, and my remainder then is 3. Now the remainder is going to go to 0 as x gets really, really large. For your oblique asymptote, what you're looking for is what's up here. So what this tells me is that y equals to whatever this result is. So this linear equation is actually my oblique asymptote. So it's not going to be a dashed horizontal line, it'll just be a dashed diagonal line. Okay? All right, now let's do some calculus. So let's go ahead and find out some of our derivatives. All right, so to find f prime, I'm going to just stick with my quotient rule on this. So I'm going to do low, which is x minus 2, times d high, which will be 4x minus 5, minus high, times d low, which is just 1, all over low, that bottom squared. And you're going to have to clean this up because you want to simplify it. So when I FOIL, I'm going to get a 4x squared, a minus 5x, a minus 8x, and a plus 10. And then I need to distribute my negative across, so minus 2x squared plus 5x minus 5. So combining like terms, 4x squared minus 2x squared is 2x squared. These 5x cancel, but I have that minus 8x left, and 10 minus 5 is 5. So here's my first derivative. Okay, where is this going to be 0 and d and e? Well, the d and e is going to happen when that denominator is 0, and obviously that's going to happen at 2. So we are going to have a critical point at x equals to 2. And again, that's technically not a point on the graph because that was our asymptote, but we do need to include it on our number line analysis. Now to do the top, you have a quadratic equation. So I'm not going to take the time to show you how to do that. It doesn't factor. You would have to use the quadratic formula. So we would use the quadratic formula on 2x squared minus 8x plus 5, set it equal to 0, and what you get for your solutions are approximately 3.22 and 0.775. So we've got 3 critical numbers to worry about. Okay? All right, now that was the first derivative. Now we need to do the second derivative. So you can do a quotient rule again if you like. That's up to you. What I'm going to do is just like what I did on the last example, I'm going to convert this first derivative into a product. So I'm going to take that 2x squared minus 8x plus 5, and I'm going to multiply it by x minus 2 to the negative 2. I usually find that doing it this way and using a product rule and then factoring makes it easier for me to simplify, but it's really your choice. So the second derivative will be this first function times the derivative of this second function. So we'll have to bring down that power and subtract 1 from the power. What's inside stays inside, and the derivative of what's inside is just a 1. Then I'm going to add to that the second function times the derivative of the first, which is 4x minus 8. So what we get now is this, and I'm just going to go ahead and factor right away. I have an x minus 2 to the negative 3 and an x minus 2 to the negative 2. So they both have that in common. Remember, you want to pull out the smaller of the two powers. So I'm going to pull out x minus 2 to the negative 3, and in parentheses I'm going to have left this negative 2 times 2x squared minus 8x plus 5. And from this second factor, I'm going to have one of these x minus 2's left. And again, that's because negative 3 plus a 1 would get me back to that negative 2. And I'm also going to have this 4x minus 8 left over as well. So distributing inside, I'll get a negative 4x squared, a positive 16x, and a minus 10. And over here, I'll get a 4x squared, I'll get a minus 8x, another minus 8x, and a plus 16. So the 4x squareds cancel. 16x minus another 16x means those guys cancel, and negative 10 plus 16 is just a 6. So we end up with a 6 from everything in the brackets here, and then all of that 6 was being multiplied by this x minus 2 to the negative 3. So when I move that x minus 2 to the bottom, this becomes 6 over x minus 2 to the positive 3. So that's kind of amazing that it simplified so nicely, but it did. So there's my second derivative. We want to know where is this 0 and where is this d and e. To be 0, the numerator would need to be 0, and that doesn't happen because the numerator is always 6. But the denominator will become 0 at 2, so we will have a critical point again at x equals to 2. Okay? All right, we've got our critical points. We're ready to put them on our number line. So I'm going to have a number line for f prime. And that was at 0.775. That was my smallest critical point. Then I had 2, and then I had 3.22, and those decimals came from that quadratic formula for where that numerator was 0. Then for my second derivative, the only critical point we had was at 2, that vertical asymptote. Okay, so now we need to test our intervals. So if I test something here, you're going to have to use your calculator for this first derivative. I'm not going to bother pulling all that up and showing you because this is going to take a really long time otherwise. But you could test something like 0. Now that one would be pretty easy. 0 minus 0 plus 5 means that numerator would be plus, and the denominator is always positive because it's a quantity squared. So this would be plus over here. Then you would have to try something like 1, and that would give you 2 minus 8, which is negative 6, plus a 5. So this numerator would become negative, and the bottom is still plus. So this is minus. Then you'd have to try something like maybe 3, plug that in, and when you plug in 3, you get 3 squared, which is 9. 9 times 2 is 18. 18 minus 24 is negative, plus another 6. That's actually negative on top. So this turns out to be minus as well. And then if you try something like 4 and plug that in, then your numerator turns back to a positive. So I'll leave that for you to check on your calculator. But we're just plugging in points into that numerator. The denominator is always plus. For the second derivative, it's much simpler because the numerator is always positive. So it's just a matter of checking that denominator. If I plug in 0, 0 minus 2 will be negative. When I cube it, it'll stay negative. So this is going to be minus. But if I tried 3, then 3 minus 2 becomes positive. So this will be plus. Okay? Now, I'm not going to write out everything like I did last time. You certainly could, but it increases where I have these plus signs right here and right here, and it decreases here and here. And then where I have minus signs, I'm going to be concave down, and where I have plus signs, I'm going to be concave up. So if I draw in my little dashed lines, at each of these critical numbers, then this will be concave down, and both of these will be concave up. Now we also had some relative maxes and mins. So if you look back at our signs, we had a plus over here and a minus over here. So that's going to be a max at 0.775 for the x value. And then at 2, we were minus on the left and then minus again on the right. So that is nothing. That doesn't have a change in sign, so it's not a critical, or excuse me, it's not a relative extrema. But at 3.22, we're minus on the left and then plus on the right, so this is going to be a min. So we'll have a relative min at 3.22 for the x value. And then we only had the one critical number for the second derivative, and that was at 2. It did have a change in concavity because it was minus on the left and plus on the right, but 2 cannot be considered a point of inflection because that was that vertical asymptote again. It doesn't have a derivative there. So we have no POIs. Okay, now the y values for these two x's, you would have to find those by plugging in those decimals into this function and figuring out what those y's are. So at 0.775, this is approximately negative 1.89, and at 3.22, it's approximately 7.89. Okay, so now if I look at my 4 options here, concave downs and concave ups, increase, decrease, decrease, increase. Then on this first region right here, concave down increasing is going to be this upper left shape. So I want to do that until I hit that 0.775. And then after that, I'm concave down decreasing, which is the other half of that hill shape. And that should make sense because remember we had a max right at 0.775. Now remember at 2 we had that vertical asymptote. So you have this vertical line shooting down, so this is probably going to be going like that. Okay? So on the other side of 2, now we're going concave up, decreasing, which would be this shape. So I need to have that shape, which means I'm going to probably be shooting up here on the left. And then we do that until we hit 3.22, and after 3.22 we're concave up increasing, which is the other half of this U shape. So like that. Okay, so let's put it all together onto our graph. All right. So the two main points that we had, 0.775, comma negative 1.89. So that's a little less than 1 on the x and almost negative 2 on the y. And then we had 3.22, comma 7.89. So that's close to 8 right up here. And then we also had an intercept from the very beginning at 0, comma negative 5 halves, which is negative 2.5. So I can plot that as well. So that would be about here. And then let's plot in our asymptotes. We had a vertical asymptote at 2. And then remember we had that oblique asymptote, and it had equation y equals 2x minus 1. So if you were to sketch that line, that has a y-intercept at negative 1 and a slope of 2. So I would go up 2 over 1, up 2 over 1. So it's going to look like this. So that's our oblique asymptote. Here's our vertical asymptote. So our graph, whatever shapes here we draw, need to sort of be squeezed in between these asymptotes. So you can probably already start to see how that's going to have to look. So on the left side of this 0.75, which was this little point right here, we wanted to shoot downwards, and it needs to be approaching this asymptote. So this is going to be going down like that. And then we have that arc going down towards our vertical asymptote. So something kind of like that. And then on the other side of 2, we came from above towards that min, and then we want to continue arcing back up again, but going towards that oblique asymptote. So you kind of get these two U shapes that are squeezed in between this sort of X. Okay, so there's our final graph. Okay, on this next example, we have the function 3x to the 2/3 minus x squared. So we're going to go ahead and start with our usual strategies. I'm going to go ahead and find my intercepts first. So if we try to find our intercepts, I can let x equal to 0. then this term would be 0 and this term would be 0, so y will be 0 as well. And so I've got my intercept, and if I try and find out my X-intercepts, then we would need to set this function equal to 0. So if I let y be 0, then this becomes 0 equals 3x to the 2/3 minus x squared, which does factor a little bit here. You can pull out the smaller of the two powers, which would be x to the 2/3. That means I would be left with this 3, and then we have to think backwards here a little bit. 2/3 plus what power would get me back to a 2? Well, if I subtracted 2/3 to the other side, 2 is the same as 6/3, so 6/3 minus 2/3 means this needs to be a 4/3 power. 2/3 plus 4/3 equals 6/3 or 2. So what does that tell me? Well, it tells me that for my two solutions, either this factor is 0, which is the intercept we already got when x is 0, y is 0, but it also gives me another solution here from this factor. When does 3 minus x to the 4/3 equal to 0? Well, if I add that x to the 4/3 over and then solve for x, I would need to undo that 4/3 power. And you can always undo powers by raising both sides to the reciprocal power. So if I raise both sides to the 3/4, then that will give me 4/3 times 3/4, which is 1. So the right-hand side will just be 1. And then the left-hand side here would be 3 to the 3/4, which is not going to be a nice number. You'd have to use your calculator to get a decimal for that. And it is approximately 2.28. And we would actually get 2 of those because we're taking the 4th root of both sides. And just like when you take a square root of both sides, you get that plus or minus sign. Same idea here as well. So there's actually going to be 2 X-intercepts at plus and minus 2.28. Now, if that's too much work for you, then you don't have to find that X-intercept. But I did want to show you that it is doable on this particular example. Now, we don't have a fraction here. We don't have a rational function, so we're not going to have any asymptotes at all. So there's going to be no vertical or horizontal asymptotes to worry about. So we're ready to just go right and jump into our derivatives. So let's find f prime of x. So the derivative of 3x to the 2/3. I'm going to leave the 3 where it is. I'm going to bring down the 2/3 power, and when I subtract 1 from the power, 2/3 minus 1 is negative 1/3. And then I'm going to subtract from that the derivative of x squared, which is 2x. So my 3's cancel, and we get 2x to the negative 1/3 minus 2x, and I'm going to factor that again. They both have a 2, and they both have an x, and I'm going to pull out the smaller of the two powers, which is that negative 1/3 power. So I would only have a factor of 1 left from this first term, minus some x's from this second term. And you have to think sort of in reverse here again. Negative 1/3 plus what would get you to just an x? Well, this would have to be 4/3. Negative 1/3 plus 4/3 is 3/3, which is that x to the first. Okay, so just rewriting this a tad, the 2 stays where it is, the 1 minus x to the 4/3 stays where it is, and I can move that x to the 1/3 down to the bottom. Okay, so here's my first derivative, and now to find the critical points, we're going to find out when this is 0 and when this is d and e. So if we go to find out when this fraction is going to be 0, that's going to happen when that numerator is 0. Which means when this stuff in parentheses hits 0. So to solve that, we're going to add that x to the 4/3 over to the other side, and to get this to be just x to the first, we need to undo that 4/3 power. So I'm going to use my reciprocal power. I'm going to raise both sides to the 3/4, which is really raising both sides to a 4th root, which is an even root. And whenever you are taking an even root of both sides, you get 2 solutions, a plus and a minus case. Just like when we take a square root of both sides, we get that plus or minus sign. So on the right hand side, the 4/3 times the 3/4 becomes x to the first, or just x, and the 1 to the 3/4 stays 1, but we get that plus or minus. So we get two critical numbers from where that numerator is 0. The denominator is going to be 0 when just x is 0. So that will give us the D&E case. So our critical points for this first derivative are 0 and plus or minus 1. Okay? Now we need to go to the second derivative. So I am going to take the help where I can get it, and I'm going to go back to my first derivative that I have right here in this circle, and I'm going to think of it this way instead so that I can use that product rule instead of a quotient rule. Again, that is your choice. So I'm going to move that x to the 1/3 back up and make it negative, and I'm going to group it with that 2 so that this is my first function and this is my second function. And I'm going to do a product rule on that. So I'm going to do first times derivative of the second plus second times derivative of the first. So second derivative will be the first times the derivative of the second. The 1 goes to 0, and the derivative of a minus x to the 4/3 is minus 4/3 x to the, when I subtract 1, I'm going to be left with a 1/3 power. So there's first times derivative of the second plus the second times derivative of the first. The 2 stays there. I'm going to bring down that negative 1/3 power, and when I subtract 1 from the power, negative 1/3 minus 1 is negative 4/3. Now let's clean this up a little bit. We're going to get a 2 times a negative 4/3 is a negative 8/3, and x to the negative 1/3 times x to the 1/3, you get to add those powers because you're multiplying the bases. And negative 1/3 plus 1/3 is 0, and x to the 0 is just a 1. So these actually end up canceling each other out. So you just get negative 8/3. Then over here, we have our minus from right here, and we have that 2/3 x to the negative 4/3, and it's being multiplied by this stuff in parentheses. So what I'm going to do next is go ahead and distribute this across those parentheses so that I can get rid of all of my parentheses. So if I distribute negative 2/3 x to the negative 4/3 times 1 will stay the same. And then negative times negative becomes positive. The 2/3 stays put, and x to the negative 4/3 times x to the positive 4/3 is that x to the 0 again. So that goes to 1. So we lose those x's again. So we have a couple of like terms. Negative 8/3 plus 2/3 is negative 6/3, which is negative 2. Now there's varying degrees of simplifying that you can do here. One thing that I'm going to do is take that negative exponent and push it down into the bottom. And then you can do some more factoring on this if you like, but I'm just going to stop here for now. And we want to know, when is this 0 and when is this D&E? Now because there is a fraction involved, we need to know when that denominator might become 0. So that's obviously going to happen when x is 0. So then we need to figure out, when is this whole second derivative going to equal 0. It's not a single fraction, it's actually a difference of two terms. So it's going to take a little bit more solving to figure out when this is 0. So what I'm going to do is take this second derivative, set it to 0. I'm going to add this fraction over to the other side. And then I'm just going to treat this like a proportion, and I'm going to cross multiply. Or I'm just going to basically multiply both sides by that denominator. So the left side will become negative 6 x to the 4/3, and the right side will just be 2. So then I divide by negative 6, which leaves me negative 1/3. And then to solve for that x, we want to raise both sides to the reciprocal power, which would be to the 3/4. Now that is an even root, so you should be getting that plus or minus sign, but we also have a problem, because over here on the right side, we're trying to take an even root, a fourth root, of a negative number. and that does not exist. That is not a real number. So I don't have any solutions to the 0 case. This doesn't happen. So the only critical points that we have for the second derivative are 0. Okay, so we're ready to set up our number line. So we're going to have f prime, and f prime's rule was 2, 1 minus x to the 4/3 over x to the 1/3, and I'm going to put on there -1, 0, and 1. And then for f double prime, we have -2 minus 2 over 3x to the 4/3, and the only critical number I have for that is 0. Now I'm ready to test my intervals. So if you test something less than -1, say -2, -2, the cube root of that will stay negative, but then we're raising it to a 4th power. So that's actually going to become positive, and 1 minus that's going to be negative. And on the bottom, -2 to the 1/3, in other words, the cube root of -2 stays negative as well. So we'll get a minus over a minus, which becomes a plus. Then if you try a decimal like -1/2, then this numerator turns into a positive. You can check that on your calculator. So this becomes minus. If we tried a positive fraction, then the bottom becomes plus because you're taking the cube root of a positive number, so the quotient becomes positive. And then if we try something bigger than 1 like 2, then this numerator goes back to being negative again, but the denominator is still plus. So this is back to minus. Okay? Then for the bottom, if we try something like -1 in the bottom, we take the cube root of it, it stays negative, but we're raising it to the 4th power. So this denominator is always going to be positive no matter what we plug in. So we're going to have a minus and a minus from this guy minus this number. So it's a -2 minus 2 over something. Those are two negatives. That's going to stay negative. We're not multiplying these, we're subtracting. So if I tried, for example, 1, positive 1, the cube root of 1 stays 1, 1 to the 4th stays 1, 3 times 1 is 3. So this is really going to be -2 minus 2/3, which as you can see will stay negative. And if I had used a -1, I get the same result because of that 4th power. So no matter what number I plug in, I get minuses for both of these. Okay? All right, let's draw in our little lines. We are increasing here and here, decreasing here and here, concave down everywhere for that second derivative because I was minus everywhere. Now if we look at our relative extrema, we do have a change in signs at -1. I go up and then I go down. So I have a relative max at x equals -1. At 0, I go down and then up. So I have a relative min at 0. And then at 1, I go up and then down again. So I have another relative max at +1. Okay? And then at 0, for the second derivative, there is no change in concavity. So that is not a point of inflection because the signs stayed the same. They did not change. Okay? So I have these three relative extrema. To find these these y values, we would just go back to our original function and plug in. So for example, if I go to here and I plug in 1, cube root of 1 squared stays 1. This is just going to be 3 minus 1, or 2. So this is 1 comma 2. And if I plug in -1, I get exactly the same thing because of those squares on top make them become positive. So this is also 2. And at 0, we had 0. That was one of our intercepts. Okay? So we're ready to put everything together onto our graph. So I have 1, 2, -1, 2, 0, 0. And we did have a couple of other intercepts, if I recall. We had when x was plus or minus 2.28, the y value was 0. So this was going to hit a little past 2 on the x-axis and a little past 2 over here as well. Okay, so let's go ahead and figure out what our shapes are going to be. Our choices are going to be these 4 pieces. So if I am concave down increasing, that's this shape right here until I hit -1, excuse me. And then I'm still concave down but decreasing, so that's this other shape, other half of that U shape until I hit 0. And then after 0, I'm concave down increasing again, so now it's this shape until I hit 1, and then back to concave down decreasing after 1. So it's going to look something like that. So we had a relative max at -1 and 1, that looks good. We had a relative min at 0. Notice that at 0 we are getting a cusp or kink in that graph, and that is okay because remember 0 came from the derivative not existing, and when you have a derivative that does not exist, then that's a kink or a cusp in your graph. So that is verified. That is exactly what we want to be seeing. So all we have to do is connect the dots. We're going to rise up to our max and then come down, and then we're going to have that cusp and arch back up again to our another max and come back down again, and here's our graph. And we do have a graph that is symmetric over that y-axis, and you could have verified that from the beginning if you did check for symmetry. You have these nice even powers of x's, which is what makes it have that symmetry. Okay, so everything looks good. All right, let's try our next one here. So this function is 10 over 2 minus 3e to the negative x over 2. It's kind of hard to read there. All right, so what we want to do is find out our intercepts, our asymptotes, and all that kind of stuff. So let's start with our intercepts. So I'm going to let x equal to 0. So this gives me y equals 10 over 2 minus 3e to the 0, because -0 over 2 is going to stay 0. And what you have to remember is that e to the 0 goes to 1. So this denominator is 2 minus 3, which is -1. So this is -10. So we have an intercept at 0, -10. Now to find the asymptotes, this is a fraction, so potentially there are going to be some asymptotes. Now the vertical asymptote is going to happen whenever that denominator is 0. So we have to do a little bit of solving here. So I'm going to take 2 minus 3e to the negative x over 2, that denominator, and I need to find out when it is 0. So let's add this 3e to the negative x over 2 over to the other side. And then I'm going to take each side and divide by 3. We're trying to isolate that e. And this is an exponential equation. So in order to solve this for the x, we have to undo the e. And what's going to do that is an ln. So at this point, we need to take an ln of both sides. And the ln cancels out the e, so this right-hand side just becomes negative x over 2. So to finish solving that for x, I can just multiply both sides by -2. So I'll get -2 ln of 2/3 is equal to x. So that's where your vertical asymptote occurs, and that is approximately 0.8109 as a decimal. And it is positive because ln of 2/3 is negative, and we're multiplying it by a negative, so it becomes positive. Okay, so there's my vertical asymptote. Now let's see if there are any horizontal asymptotes. Now remember, to find horizontal asymptotes, you're taking a limit. And this one is not a rational function, it's an exponential function. So you could get different answers depending on whether you go to positive infinity or whether you go to negative infinity. So we are going to have to look at both directions, because sometimes you get more than one horizontal asymptote, especially if it's not a rational function. Okay, so if you were to plug in essentially infinity, think about what this would do. You have e to the negative infinity over 2. So this is kind of like 10 over 2 minus 3 times e to the negative infinity, essentially. Now think about what the graph of e to the x looks like. Nice exponential graph. So what would e to the minus infinity look like? Well, minus infinity would be this way. So what is this graph doing as they go towards minus infinity? E to the minus infinity is getting smaller and smaller and smaller and going to 0. So this goes to 0, which means we get 10 over 2 minus 0, which means we get 5. So we have a horizontal asymptote at y equals to 5. Now let's go in the other direction. So now we're going to plug in minus infinity. Now what that's going to do is when we do minus a minus infinity, then this is going to be like 3e to the positive infinity. So what does this graph do as I go to positive infinity, which would be this way? This is shooting up towards infinity as well. So this is going to infinity. So we have 10 on top, and we have something going towards a negative infinity on the bottom. A constant over something getting bigger and bigger and bigger, even if it's in the negative direction, is going to get smaller and smaller and smaller. So we have a second horizontal asymptote at y equals to 0. So we have two different horizontal asymptotes depending on which direction we are approaching. Okay? Now let's do our derivatives. Okay, so first derivative. To make my life here a little bit easier, what I'm going to do with my function is take that whole denominator, wrap it in parentheses, and raise it to the negative 1. And now I'm going to take the derivative of that. So I'm going to bring down the negative, which makes it negative 10, and inside stays the same. I'm going to subtract 1 from the power, so the new power is negative 2. And then I need to multiply this by the derivative of what's inside. Now the derivative of the 2 goes to 0. The minus 3 stays put. And then be careful here, this is e to the stuff. So its derivative will be e to the stuff back again times the derivative of that stuff. And the derivative of negative x over 2, that's like a negative 1/2 x. So the derivative of negative 1/2 x is a negative 1/2. So there's my derivative. Now we just need to kind of clean it up here a little bit. So we have a negative 10 times a negative 3, which is positive 30, times a negative 1/2, which is going to give me a negative 15. And then I have that e to the negative x over 2 from right there. And then I'm going to take all of this and move it back down to the bottom. And then if you want, you can take this e to the negative x over 2 and move it to the bottom as well. So it becomes e to the positive x over 2, and then 2 minus 3 e to the negative x over 2 quantity squared. Okay, so the question then is, where are the critical points? Where is this 0 and where is this dne? Well, to be 0, the numerator would have to be 0, and that can't happen because that numerator is always negative 15. So this doesn't work. Where is the denominator going to be 0? Well, think about e to the x over 2. That's just like a normal e to the x graph, but we have a little bit of a shrink there. What is where does this graph ever hit 0? It doesn't. It gets closer and closer to it, but it never actually does. So this won't ever equal to 0 from that part. But this inside stuff will equal to 0, and it equals to 0. We actually already solved all that up here at the very beginning. That equals to 0 at that X-intercept, which was, at that vertical asymptote, which is at that point 8109. Okay, so negative 2 ln 2/3 was this solution. So this equals to 0 at negative 2 ln 2/3, which is approximately 0.8109, that vertical asymptote that we had. And this didn't happen, so we don't have to worry about that. Okay? So our only critical point is going to be at this 0.8109, that vertical asymptote. Okay, now the second derivative is certainly doable, but we're going to sort of skip some of the work here because it gets quite messy, and I'm just going to tell you what that second derivative turns out to be, all nice and cleaned up. And the way that I end up getting it is I take this denominator and I move it back up to the top and make it have a negative 2 power, and then I just use a product rule. So it's certainly doable, but you get lots of terms and you have to do lots of factoring, and it's just a bit messy. So the end result here is that the second derivative is 15 3e to the negative x over 2 plus 2 all over 2e to the x over 2 times 2 minus 3e to the negative x over 2 quantity cubed. So then the question is, when is this 0 and d and e? So let's do the d and e case first, because it's just like the one we talked about. E to the x over 2 will never hit 0, it just approaches it. So that's not going to contribute any solutions. And this factor, this denominator here, equals to 0, again at that negative 2 ln of 2/3, or 0.8109. So we will have one critical number at that 0.8109. To find out where this fraction equals to 0, we would need to set this factor on top equal to 0. So let's try that. So to solve, I would subtract 2 and divide by 3. And without spending too much time on this, think about this a little bit. E to the negative x over 2, the graph of that, that's an exponential decay kind of graph because you have a negative up there. So this is a graph that looks something like this. When is that graph ever going to hit a negative value? It doesn't. So this has no solutions. E to the negative x over 2 is always positive, so there's no way it can be negative. So we don't have any places where this second derivative will be 0, so our only critical point is going to be at that 0.8109 again. Okay? So we're ready to make our number lines. So for our first derivative, the only critical point that we had was that 0.8109, and that was also the only critical point we had for our second derivative as well. So here I would recommend digging out a calculator to do your testing. If I tried 0, for example, into this, that would be a number less than 0.801. The top is obviously negative. E to the 0 is 1, so that'll be positive, and this quantity is being squared, so that'll be positive. So this whole thing will be minus. Now if I tried something like 1, positive 1, the numerator will still be negative, e to the 1/2 is positive, and this quantity is still squared, so that will also be minus. Okay? Then if I tried 0 down here, 15 is positive, e to the 0 is positive. When I multiply that by 3 and add 2, that'll be positive. In the denominator, e to the 0 is positive. E to the 0 right here will be 1, and 2 minus 3 would be -1, and -1 cubed stays negative. So that's actually going to give me a minus sign. But when I go to the other side and try, say, +1, the top will still be positive, but on the bottom you'll get e to the -1/2, and when you multiply that by 3, it becomes less than 2. So this actually ends up being a positive number, so when I cube it, it stays positive. So this side turns out to be plus. And again, you can verify that on your calculator by punching in some numbers. Okay? So if we look at our number line here, for the first derivative, I'm decreasing here and here. For my second derivative, I'm concave down here and concave up here. We're not going to have any maxes or mins because on our first derivative number line, there was no change in signs. I'm decreasing everywhere. And unfortunately for the second derivative, I don't have any points of inflection, even though I do change concavity, because at 0.8109, that was that asymptote that we had. So it's not a point because it's an asymptote, so we can't have a point of inflection there. So if we think about concave down and decreasing. So here's my choices. Concave down, decreasing would be this shape, coming in towards that asymptote. And then on the other side, I want to be concave up, decreasing, which is this shape over here. So let's see if we can piece together some of these ideas. So 0.8109, that's a little less than 1, and that was my vertical asymptote on my graph. And then if you remember from earlier on, we did have two different horizontal asymptotes. We had 5 as we go to the right towards positive infinity, and 0 as we go to the left towards negative infinity. So I'm going to have 5 that I want to be approaching as I go this way, and then 0 that I want to be approaching as I go to the left over here. So we want to draw this shape over here somewhere so that we're bounded by these asymptotes. And remember, as we go to the left towards minus infinity, we're supposed to be approaching this 0 horizontal asymptote. So this is going to have to look something like this, towards that asymptote and towards that asymptote. But then on the other side, I want to have this arcing shape, but I want to make sure that I'm approaching the upper asymptote 5. So I'm going to have to start from above it and approach it from above, just like that. So here would be my graph. Okay? All right. This next example is a little bit different. Here we have 3 graphs given to us, A, B, and C. And one of these is the original function f, one of these is the first derivative f prime, and one of these is the second derivative. And we need to figure out which is which. So how are we going to decide which one is which? Well, one of the things that we often want to look for in a problem like this is realizing that if you have a horizontal tangent line on a graph, which would happen at either a maximum or a minimum, then its derivative, its corresponding derivative, needs to be 0 at that same max or min. So for example, right at C, at this little peak, I see a nice horizontal tangent line. And if you look down, that corresponds to a 0 right on the graph of B. And if you look at the slopes of all these tangent lines on the graph of C, they are all positively sloped lines, which corresponds to positive y values to the left of that 0 slope. And then on the other side, when I draw in these tangent lines on the graph of C, notice that they all are negatively sloped lines. They are falling. And that corresponds to all of these y values here being negative. So what that tells me is the derivative of the C graph equals the B graph. Okay? So when I take the derivative of this C and look at all those tangent lines, those slopes get plotted as the y values on the graph of B. So we have one sort of connection going on right there. Now we haven't looked at A at all yet, so let's see how A fits into the mix. So what I'm going to look at are, again, those tangent lines. And if I can find a place where one of these graphs has a horizontal tangent line because it has either a max or a min, and that corresponds to a 0 on another graph, then that's a good place to start. So again, right here is a 0 on A, and it just so happens to line up with this horizontal tangent line right on the graph of B. And let's verify to the left and to the right here a little bit. All of these tangent lines on the graph of B to the left of that minimum are all negatively sloped lines, which corresponds to all of these y values being negative. If I go to the other side and draw in these tangent lines, each of those is a positively sloped line, which corresponds to all of these y's being positive. So the derivative of the B graph gives me the slopes that I plot in A. Okay? So the letter here that gets used twice is going to be our middle function. So we're going to let B be our f prime. So if the derivative of B is A, then the derivative of f prime would be f double prime, and that needs to be our A. So graph A must be the derivative of B, which means the derivative of the derivative, or the second derivative. And going backwards here, B is supposed to be the derivative of C, so C must be the original function so that when I take its derivative, I end up with B. So these are how the three functions are labeled. C is the original, B is the first derivative, and A is the second derivative. Okay, on these last examples here, again, it's a little bit different than what we've been doing. We're going to be graphing our original function like we have been doing, but we don't have a formula to work with. All we have to work with is an actual graph. So on this first one, this graph that we see right here is actually the graph of the first derivative, f prime. So this is f prime right here. And based on that, we want to work backwards to figure out what the graph of the original function f is. And the best and easiest way to do that is to use those number lines. So from this graph right here, I can create a corresponding number line for f prime. Now be careful here, because what we're looking at is the actual graph of f prime. So when I put my critical numbers on my number line for f prime, that's usually wherever that derivative is 0 or d and e. And where does this graph hit 0 or become undefined? Well, it's never undefined, but it hits 0 here and here. So those are the critical numbers, -1 and +3, of the original function f. Okay, they're not the critical numbers of this graph. They're the critical numbers of this unknown graph f that we're trying to figure out. So the zeros of this f prime graph should be the numbers that you put on your number line. Then to figure out the signs, normally we would want to put pluses and minuses up here. The signs that you're going to put here come from the y values of this graph. So all of these y values are negative because they're below that x-axis. So that's why we're going to put a negative right here. All of these y values are positive because they're above the x-axis. So that means the derivative should always be positive there. and then all of these derivatives, or excuse me, all of these y values are negative again. So we're back to a minus sign. So that's how I create a number line for the first derivative. Now, to get a complete graph of f, I also need to know a number line for the second derivative as well. And I don't have the graph of that second derivative on here. So let's figure it out. Okay? So the way we do that is the way that we've learned way back a few lectures ago. To find out the derivative graph, you want to sketch in those little tiny tangent lines. Wherever you see a zero slope or a horizontal tangent line, that is going to be a 0 y value on the derivative graph. All of these slopes are positively sloped lines, and as I go from this 0 out, it becomes positive, a little more positive, a little more positive, and steeper, steeper. So this is going to go positive, positive, more positive, steeper, steeper, just like that. On the other side, I start at 0, and then I have a little negative slope, a little more negative, a little more negative, and these get steeper and steeper, but in the negative direction. So this is going to go down like that. Now, since the graph that we were starting with was already f prime, then the derivative of that will be f double prime. So now you want to focus on this blue line and use that information to fill out this number line. Remember that the zeros of this graph are going to be the numbers you mark on that number line. So the only 0 that this line has is right here at 1. To the left of 1, all of these y's are positive, so I'm going to put a plus sign. To the right of 1, all of these y's are negative, so I'm going to put a minus sign. So now we have our two number lines, so we should be able to get the graph of our original function f. And the way we do it is just like we've been doing it today, sketching in all of our different possible shapes. So I'm going to put in my little lines for each of those critical numbers. This is decreasing, increasing, increasing, decreasing. This is concave up, and then concave down, concave down. So out of my 4 choices, we want to start out concave up, decreasing. That would be this shape right here until I hit -1. Then between -1 and 1, I want to be concave up, increasing, which is the other half of that U shape, until I hit 1. Then after 1, I want to be concave down, increasing, which is this shape, until 3. And then after 3, concave down, decreasing, so back down like this. Now, they don't tell me any specific points for how to plot these. I don't know how high I'm supposed to plot -1 or +1 or 3. They don't tell me any of these y values. So we can't really place this per se on our graph. So usually what I do for my answer is I don't even really put my axes down. I just show this shape and I just kind of show it along that x-axis where this was -1, this was 1, and this was 3. And if you want to put in your y-axis, somewhere over here, you can, but we don't necessarily know how high or how low this graph is, or how steep or high that peak or how low that valley should be. So the best you can do on these kinds of examples is just show the general shape, but not necessarily with as much accuracy as possible, because we aren't told enough information to be able to plot exact points. So this is the shape of our original function, f of x. Okay, let's try that again on this next example. All right, so this is f prime of x. So right away, on my number line for f prime, we want to put down our critical numbers. When you're looking at the graph of f prime, you want to know, when is this f prime graph 0? Well, it's 0 at 1 and 4. So those are going to be the critical numbers that we write down. To the left of 1, these are all positive y values, so I put a plus. Between 1 and 4, again, these are all positive. But after 4, these become negative. So that's how I figure out my number line for f prime. Now I need to figure out my number line for f double prime, which requires knowing the graph of f double prime first. So to figure that out, we're going to sketch in those little tiny tangent lines. Now I have a couple of 0 slopes right here, so that's going to be a 0 on my derivative, and right here is going to be a 0. To the left of 1, all of these slopes are negative, and they're getting more negative as I go to the left. So I go down negative and I get more negative as I progress to the left. Between 1 and 3, all of these slopes are positive, but they sort of peak in the middle here. They go positive, positive, positive till 2, and then I have to turn back around again, still being positive but not as big, so that I can come back around to that 0 slope. So this is going to have a little arch to it. And then after 3, all of these slopes are back to being negative again, and they continue to get more negative as I progress. So this graph in blue is f double prime. So to get the number line, we're looking for where this blue graph equals to 0, which is 1 and 3. So 1 and 3. To the left of 1, these are all negative. Between 1 and 3, these are all positive. And after 3, these are back to being negative again. So there are my number lines. So now let's break this up. And here I'm increasing, 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 decreasing. Here I'm concave down, concave up, concave down, concave down. Okay, so if I put my pieces together here, here's my 4 choices. Concave down, increasing would be this shape right here until I hit 1. And then concave up, increasing would be this shape until I hit 3. And then after 3, I'm concave down, increasing, which is this shape, until I hit 4. And then after 4, I'm concave down, decreasing, like that. So my general graph for f is going to have this sort of shape to it. And I'm not even going to bother to put any axes on there. There is my f of x. Okay? Alright, let's try one last example. Okay, so here again is the graph of f prime. So immediately on my number line, the zeros that this graph has are the places where f prime equals 0. So that's at 1 and at 4. To the left of 1, my y's are negative. Between 1 and 4, these f primes are positive. And after 4, the f primes are still positive. So there's my first number line. Now let's get a graph of the second derivative. So sketch in those tangent lines. I have a 0, 1 here, so that's going to be a 0 slope, and a 0, 1 here, so that's going to be a 0 slope. To the left of 2, all of these slopes are positive, and they get more and more positive as I go to the left. So I'm going to go positive and get more and more positive as I go to the left. Between 2 and 4, I start at 0, and then I get a little negative, a little more negative, and then right at 3 I'm sort of my most negative, but then I have to come back down again and hit 0. So I'm going to go negative, negative, negative till I hit 3, then I have to turn back around again to hit 4. And then after 4, these are all positive slopes again, and they're getting bigger. So this is going to go positive and continue to get bigger. So this graph in blue is f double prime. So my number line for f double prime, I have a 0 at 2 and a 0 at 4. To the left of 2, all of these f double primes are plus. Between 2 and 4, all of these f double primes are minus. And after 4, all of these are plus. So we're ready to get our pieces together. Okay, so I'm going to have 1, 2, and 4. This is down. These are both up, and this is up, and this is concave up until I hit 2, then I'm concave down, and then I'm back to concave up again. So concave up decreasing is this shape right here. So I want to do that until I hit 1. Then I'm concave up increasing, so this shape until I hit 2. And then after 2, concave down increasing, which is this shape, until I hit 4. And then concave up increasing, which is this shape, and I go like that until the end. So my graph of f is going to look something like this. We have a min at 1, we have a point of inflection at 2, and another point of inflection at 4, and it's going to have this shape. So there is the graph of f of x. Okay? Alright, this curve sketching stuff takes a lot of practice. There's a lot of arithmetic that has to be done to do these derivatives, so go slowly and be very careful, especially with checking your signs and getting your pluses and your minuses. Because if you screw those up, it's obviously going to change what shape you're supposed to be piecing together. Good luck!